you recall, we have been talking about various algebraic methods of manipulating switching expressions, switching functions, and also we saw that using some basic rules or theorems, we can apply them in a suitable way to reduce the number of product terms, reduce the number of literals, which means some sort of minimization. So, today we start our discussion on some more systematic ways of minimizing switching functions, which in the algebraic form is a little complicated or complex. So, the method that we shall be starting with is using something called Karnaugh maps, minimization using Karnaugh maps. This is what we shall be starting our discussion on. So, first let us try to understand what is a Karnaugh map. First thing, let me tell you, Karnaugh map is some kind of a visual or graphical representation of the function. See, any function, any switching function that you want to minimize or manipulate, we should be able to express it in some way. We have already seen some of the methods like the truth table, like the sum of products or the product of sum expression forms. Now, Karnaugh map is another way of representing a function, which is visual or pictorial in a sense that all the minterms of the function can be represented in a matrix form and all the true minterms are marked in that matrix. Depending on the positions of the true minterms and their relationships, we can apply some simple rules to create some kind of minimization procedure, so that what we will get finally will be the minimized form of expression, either sum of products or product of sums. So, basically speaking, what I am talking about is that Karnaugh map is nothing but a graphical method for representing and minimization of functions. Well, we use Karnaugh map for simplifying or minimizing switching functions. We earlier already have seen how we can use algebraic technique to do the same, but instead of algebraic methods, we would be using this Karnaugh map, which I shall said is some kind of a pictorial representation, and sometimes in short we refer to it as K map. Okay. So, there are some characteristics of a Karnaugh map that I would like to talk about. Well, let us consider we have an n variable function. I have an n variable function. So, obviously, there will be 2 to the power n minterms in this function. So, in the Karnaugh map, there is a concept of cells, and the cell has a 1-to-1 correspondence with these minterms. There are 2 to the power n minterms. The K map will also be having 2 to the power n cells, and these minterms are mapped to the cells in a very specific way, such that the adjacent cells, let us say adjacent 2 cells, pair of cells will differ in only one variable. Like let me take an example. Suppose in a 3 variable function, one cell corresponds to A B C bar and its neighboring cell may correspond to A B C, where C is the only one variable which is differing, right. Similarly, in the Karnaugh map, we can also talk about 2 square or 4 cells. Now, if we have a set of adjacent 4 cells, they will be differing in 2 variables. In general, we can have any power of 2 to the power m cells, which will be differing in m number of variables. So, this we shall be seeing through examples. So, what we try to do is, we try to group these cells. Now, as I said, we have the Karnaugh map, we have these cells on the map, where each cell corresponds to a minterm. We try to group these cells together, and each group will be having 2 to the power m adjacent cells, some power of 2, okay? 1, 2, 4, 8, 16 like that. So, we try to group some adjacent cells which are some power of 2 corresponding to the true minterms, and we always try to make the size of these cubes bigger, because bigger the number of cells in a group, more the minimization that we have been able to achieve. So, our target will be to make these cubes or these groups as large as possible. Okay? This is our basic objective. So, now the question is, how do we label the cells in a Karnaugh map such that this property is ensured? Now, this is something which I have already mentioned, that we have mapped the minterms to the cells in such a way that a pair of adjacent cells will differ in only one variable, right. Now, if we can have that, for example, I will show you how a cube looks like. Suppose I have a cube like this, let us say it is a 4 by 4 cube. Let us say I have one cell out here, one cell out here, these two are adjacent cells. Let us suppose this one of this cell corresponds to the minterm A B C, the other one corresponds to the minterm A B bar C, which differs in only one variable B. So, I am saying that if I have a pair of such neighboring true minterms, I can combine them into one. So, the idea of combining is this: if I combine them, then you see the rule of simplification, if you take A C common, this B and B bar will cancel out, this will of course C is missing, this will be A C. Okay. So, if you take A C common, B plus B bar, this will be A C. So, there is a minimization. Similarly, if you have 4 such cubes together, let us say these two in addition this and this. So, there is a bigger cube I can form of size 4. Then these 4 cells may correspond to these 4 minterms, and using rules of switching algebra you can easily see by combining them in pairs that this is ultimately equal to A. So, you see the bigger the size of the cube, more is the minimization. If you can combine 2 cubes, I have something like A C. If I can combine 4 cubes, I have only a single literal. So, the number of literals go on decreasing as we make the cubes larger and larger. Suppose originally I have an invariable function. If I make a 2 cube, it becomes n minus 1. If I make a 4 cube, it becomes n minus 2. If I make a 8 cube, it becomes n minus 3, and so on. So, cubes will become smaller and smaller. Okay. So, this Karnaugh map is fine, but of course, there is some drawback also. The main drawback is that because it is a pictorial approach, well, we cannot draw a figure like that with more than 5 or at most 6 variables. Well, even with 5 variables it becomes complicated. So, here all the examples that we shall be showing will be up to 4 variables only. Okay, 5 and 6 variables becomes complicated, beyond 6 it becomes impossible. This is the main drawback of Karnaugh map. Now, let us see what is the basic approach in this method, the Karnaugh map based minimization method. So, what we do, as I said, Karnaugh map is a 2-dimensional matrix of cells. We try to fill up the cells with the true minterms of the function. I shall be illustrating this with an example. So, each cell corresponds to minterms. So, we consider only the true minterms, which are the minterms that are 1 for the function. So, we mark those true minterms, and then we try to group these true minterms based on their neighborhood. So, as I said, I can group 2 of them together, I can group 4 of them together, I can group 8 of them together, and so on. So, this grouping will be carried out in such a way that we shall be trying to make the cubes as large as possible. We shall be trying to maximize the size of the cube, and also we should ensure that every true minterm in the function should be covered by at least one cube. Okay? So, once we have done that, every cube will be corresponding to a product term. We create one product term out of every cube. So, once we have done this, grouping the true min terms into cubes, so every cube will correspond to one product term, and what we get will be the minimized sum of products expression for the given function. This is the basic approach behind the Karnaugh map method. Let us take a simple example to start with. We consider 3 variable functions to start with. Later on we shall be extending it to 4 variable and see how it looks like. So, in this example that I am showing here, I am considering a function, any function of 3 variables a, b and c. So, the Karnaugh map of a 3 variable function will obviously contain 2 to the power 3 min terms, which is equal to 8. This is organized in this way, let us say 2 rows and 4 columns, and I am labeling the rows and columns by the variables. Since there are 3 variables a, b, c, so along the rows I am using a, along the columns let us see I am using b and c. Well, here I can use other way around also, but here in this example I am assuming that a is marked in the row and b and c are marked in the column. Now, one thing you see, the rows indicate the value of a. If the value of a is 0, it is first row. If the value of a is 1, it is the second row. Similarly, with respect to b c, you see the 4 combination of values 0 0, 0 1, 1 0 and 1 1 are given. But the point to note is that you see we have not written these values in the binary value order 0 0 0 1 1 0 1 1. Rather, we had written this 1 1 first and then 1 0. So, why we have done this? Because we have to ensure also, as I had said, that 2 adjacent min terms must differ in one variable only. Okay? Suppose if I write 0 1 and just on the right of it I write 1 0, then if I consider 2 cells, one cell here, one cell here, this cell corresponds to a equal to 0, b 0 and c 1, and this cell if it is 1 0, then it will correspond to a 0, b 1 and c 0, which means in one case it is 0 0 1, in other case it is 0 1 0. So, you see they are differing in 2 variables. So, you cannot do this. So, we write or label the columns in some kind of gray code count order 0 0 0 1 1 1 1 0. So, that they vary in 1 bit position across columns. Not only that, another interesting point to notice that you see you can assume that the right side and the left side also are neighbors. How? You see this is 1 0 and the leftmost column is 0 0, they are also differing in one position. So, right and left will also be considered as neighbors. Similarly, top and bottom will also be considered as neighbors. Well, here in the rows you have a only, so it will always differ in one position. Suppose this and this, it will correspond to 0 1 0, the first one, the second one will correspond to 1 1 0, they will differing in one position, right. So, this is how we make the labels, and the corresponding decimal numbers corresponding to the values of a, b and c. So, if I write down the decimal values of a, b, c like in this order, then they will be written like this 0 0 0 is 0, 0 0 1 is 1, 0 1 0 is 2, 0 1 1 is 3, similarly 4 5 6 7. So, when you use a Karnaugh map, you should be remembering these assignments of the decimal equivalent of the min term values. Okay? 0 1 2 3 4 5 6 7. Okay. Now, let us take some examples of actual minimization, how you can use this to minimize functions. Let us start with a very simple example here. So, you see here I have shown a function of 3 variables. We write it like this, let us say a function of 3 variables a, b, c. There are 4 ones, meaning there are 4 true minterms. So, we write it like this, sigma notation, this means these are the true minterms. So, what are the values? 0 0 0, in decimal this means 0, 0 1 1 it means 3, 1 0 0 it means 4, and 1 1 1 it means 7. So, this problem of the function I can also express like this. It is a sum of the minterms, the combination, there are 4 true minterms corresponding to the decimal values 0, 3, 4 and 7. Now, one thing you see before you go into the Karnaugh map, 0 means what? All 0 0 0, which means a bar, b bar, c bar. 3 means 0 1 1, which means a bar, b and c. 4 means 1 0 0, a, b bar, c bar, and 7 means 1 1 1, a, b, c. Now, if you use normal algebraic methods, then you can see that the first and the third one b bar c bar is common. If you take it common, you get a bar plus a, which is equal to 1. So, you get only b bar c bar. Similarly, the second and fourth, if you combine, b c is common and a bar will go, you get b c. So, the minimized form will be, according to algebraic technique, you will get b bar c bar or b c. Let us verify how you can get the same thing from Karnaugh map. Now, see, I have shown the true minterms here. Let us try to form the cubes. The rule of cube formation is, as I said, the number of cells should be some power of 2, they should be adjacent to each other, and you make it as large as possible. Okay. So, here you can see one cube can be like this, one cube can be like this. You cannot make them any bigger, right, because these adjacent cells are empty. Now, when you make these cubes, say for this cube, you see it is spanning both the rows. So, a 0, a 1 both it is covering. So, a is getting cancelled out. You have b c 0 0. So, this corresponds to b bar c bar, and this one again a cancels out 0 and 1, and it corresponds to 1 1, which is b and c. So, these two cubes correspond to these two product terms. So, the sum of product expression in minimized form will be b bar c bar or b c. Okay. So, in Karnaugh map you get the same value, but you do not have to make any algebraic manipulation like here, directly you can get it, right. Let us take some more examples. Let us take an example like this. See, here there are 5 true minterms. So, instead of going into the algebraic thing, let me straight away come to this map method. So, you see that if you want to make the cubes, I can make a cube like this, I can make a cube like this. So, every minterm must be covered by at least one cube. So, this is uncovered. So, maybe I can make another cube like this. Suppose I do it like this. So, all the minterms are covered, then what will be the expression for the first cube? This will correspond to b bar c bar. For the second cube, you see this is in the first row. Okay. First row means a bar, a is 0, and it is covering 0 1 and 1 1. So, the first one gets cancelled out, second one remains, which means c remains. This is a bar c, and this one is a bar, c cancels out, b remains, a bar b. So, there are 3 terms. Okay. But the point is, notice that this is not minimal, because I could have made the cubes even larger. This is just an example I have shown, but this is not the right process. So, if you want to follow the right process, the cubes will be, this is one cube and this should be one cube, all 4 cells together. because as I told you, you can combine any power of 2 number of cells as long as they are adjacent. So, if you do this, the first one will correspond to again B bar C bar, second one will correspond to, it is the first row. So, there will be A bar and it is covering all 4. So, B and C all cancels out. So, only A bar remains. So, the expression is B bar C bar or A. This is the minimized expression. So, directly from the Karnaugh map you can get this, right. Let us take another example. Well, here again let us see one cube you can notice like this, these 4. Now, you may tell that well I can see one cube here, I can see one cube here. Suppose I do this, then this first cube will be corresponding to A gets cancelled out 0 0, this is again B bar C bar, the last cube again A cancels out 1 0. So, it will be B and C bar, and this big one will be only A bar, because B C both cancels out, it becomes like this, these 3 terms. But what I am saying that this is not minimized. As you can see, this B bar C bar and B C bar can be further minimized. Algebraically, if you take C bar common, then B vanishes, right. If you take C bar common, it will become B bar or B. This will become 1. So, only C bar will remain. So, this is not the correct way of cube formation again. The correct cube will be, this is of course as large as possible you can make, but you remember that I said that the rightmost edge and the leftmost edge are they are adjacent. So, you make a cube like this, these 2 fellows here and these 2 fellows here, these 4 together they are adjacent, right. So, if you do this, then this cell A cancels out and 0 0 and 1 0. So, B cancels out and C is 0, C bar, only C bar, and this one is only A bar. So, it is C bar or A bar. This is the minimized form, right. So, you should notice or note that when you create these cubes, your cubes should be as large as possible, you try to make them as big as possible, then only you will get the minimized form. But you see the advantage, I do not have to go through any algebraic technique, just pictorially you form the cubes and directly write down the product terms from there. Okay. Let us take some more examples. See, here I have an example. So, here again I can form a cube with these 2 and these 2, a cube of 4. These 2 ones are still remaining. So, this one has only neighbor with this and this one has only neighbor with this, I cannot do any further. Okay. So, here it will be corresponding to this one, it will be C bar as before, this smaller cube will be A bar and 0 0 and 0 1, C cancels out B bar, and these 2 it is A equal to 1, which means A, and 1 1 1 0, C cancels out, B is 1. So, B, this is the minimized expression. This cannot be minimized any further, right. Okay. Let us continue with our examples. Let us now look at a circuit which you already seen earlier. We talked about a full adder. So, you recall what a full adder is. A full adder is a circuit which takes 3 inputs, 2 binary numbers A and B and 1 carry input, let us call it C. And in the output we get a sum and we get another carry, right. So, earlier we had shown the truth table of a full adder. So, if you check the truth table, if we look at the sum, if we consider the values of A, B and C. So, when will the sum be 1? sum will be equal to 1 only for the min terms 1, 2, 4 and 7. 1 means 0, 0, 1, 2 means 0, 1, 0, 4 means 1, 0, 0, 7 means 1, 1, 1. So, only under these 4 conditions sum will be 1. This we have depicted in the truth table like this 0, 0, 1, 0, 0, 1 this one, 0, 1, 0, 0, 1, 0 this one, 1, 0, 0, 1, 0, 0 this one and 1, 1, 1, 1, 1, right. Similarly, for a carry, if you look that when carry will be generated when the min terms are 3, 5, 6 or 7. 3 is 0, 1, 1, 5 is 1, 0, 1, 6 is 1, 1, 0 and 7 is 1, 1, 1. So, this we have depicted in this Karnaugh map 0, 1, 1, 1, 0, 1, 1, 1, 0 and 1, 1, 1, right. Now, if we try to minimize, you see for sum there are no two adjacent ones which can be combined. So, this is a peculiar scenario where no minimization is possible. So, each true min term will be a separate product term. So, if you straight away write down, first 0, 0, 1 will be A bar, B bar, C, second one will be 0, 1, 0, A bar, B, C bar, then plus will be 1, 0, 0, A, B bar, C bar and the last one will be 1, 1, 1, A, B, C. This will be the form which cannot be minimized. Now, you please note that this is a very peculiar case of a function which is nothing but the exclusive OR function of these 3 variables. Now exclusive OR is a kind of function which cannot be minimized any further in the sum of products form. So, this shows like that. Okay. But carry you can minimize, carry you see there are distribution ones are like that, you can make 1 cube like this, you can make 1 cube like this, you can make 1 cube like this. You see some of the true min terms might get covered by more than 1 cubes, no problem, but you should ensure that all the true min terms are covered. So, here what will be the function? Let us take one by this one, A is cancelled, only B C, this is B C plus this one A is 1 and 0 1 1 1. So, it is C and the last two again A is 1 and 1 1 1 0 which is B. This is the minimized expression for carry. Okay. So, for a full adder you can try this minimization procedure and get the minimum possible realizations. So, with this we come to the end of this lecture, where we have basically introduced the Karnaugh map approach and using examples we illustrated how we can minimize a 3 variable function. Now, in the next lecture we shall be extending this discussion to cover 4 variable functions. So, we shall be talking about how a 4 variable Karnaugh map looks like and how we can carry out minimization using that. Thank you.